Hi everyone. Today what we're going to be talking about is the full process of sketching polynomial functions. And so what we're going to do is we're going to go start to finish on a number of different problems. But what we're going to look at is the sketching process. So depending on what information you've been given is going to determine kind of the process that you need to go through. The processes are very, very similar. We just have to be conscious of what information was I given and therefore what do I need to do. So if you take a look at the screen that you have in front of you, in blue, you're given kind of the first process. And you'll notice it says if given the equation of the function. So if you are given the equation of that function in any form that it's been given, then there are the three things that you have to kind of do. It's not always going to feel like 3 items on a list, but it's going to be kind of a step-by-step process for it. And so what you'll kind of see is that step-by-step process. That is, you got to find your zeros. This part is almost intuition now. Us using the degree and the leading coefficient to figure out what is it doing at its extremes, its end behavior. And the only thing that's different for us now is the idea of labeling a y-intercept. So there's your process if given the equation. I can give you the function, but in a different form, that being a set of points. We've spent some time dealing with, okay, if I have a series of points that a curve passes through, well then we have a slightly different approach, but you'll notice it's pretty much the same. The only big change is the first one. We first have to figure out what degree it is, and then we can go through and find the zeros, deal with end behavior, label a y-intercept. The biggest part that I want us to get right now is that we are not able to sketch a curve with absolute certainty yet. We're not. We don't have the ability to do that. We have the ability to get pretty close, but there's some information that's going to be missing. In that blank space just on the right, I'm going to put on a quick set of axes, just so that we can all be clear on what I'm talking about when I say that we can't sketch something with absolute certainty. That I may have a curve that I've determined does something like this. By figuring out its cubic, by finding the zeros, by using end behavior, and by labeling a y-intercept. What we don't exactly know, though, is like how steep should the curve be? Maybe it should have been something like that. And what I'm getting at is we don't know what the actual position of that like little vertex is right there, or the vertex here. Like I don't know the coordinates of that point. Well, that's what you do in calculus. That actually where we sketch in this course ties directly with your curve sketching in calculus. And finally, by both topics, do you really get to the point where you have a pretty good sketching algorithm. So for our purposes, we're not overly concerned about how high a certain maximum is or how low a certain minimum is. As long as we have the proper zeros, the end behavior, and we've labeled a y-intercept, then we are good. Okay, let's get into some sketching. What you see on the screen now is going to be the 5 functions. Those are the 5 functions that we're going to go through and we are going to sketch. So this is all on one screen. At some point, I want you to pause this video and you're going to go through and you're going to try to sketch all 5. If things start to go a little rocky, then just come back to this portion of the video. Make a little note at what time it occurs so you can hop back. And then we get some things cleared up and then you try to finish them off again. So let's just say that we struggle a little bit with A and we want to check our solution to A. Well then, once you're done, then go ahead and fast track to the end of A. You want to go through B, but say you hit a snag on B. Okay, well then pause the video and jump back to this moment. As soon as you are all good, and you figured out you now saw your solution to B, then jump back to this moment in the video, get what those other ones are, and you're good. Worst case is screenshot this screen right here, and now you know the 5 functions we're going to deal with. Okay, no more blabbing. Let's work our way through these 5 functions. And so what you see on the screen right now, there is that first function. And so everyone should have paused the video and you should be working your way through a sketch. So I am simply taking up the solution to this sketch. I'm going to talk about my process, but we're going to work through some things pretty quickly. So for me to come up with the zeros, that's my first process. I want to be able to factor this. So the first thing I should have noticed is that every single one of these terms have a common factor of x. And so if I factor out that common factor, yikes. If I factor out that common factor from all terms, I get to that point. Now I look at it, I need to fully factor it. I do notice I have a cubic in there. It will not factor by grouping, so I'm going to try some factor theorem. So I look at my coefficients. If I can sub in a -1, then I think that gets us to a 0. And therefore, x plus 1 is a factor. And so, if I go through and I factor that, then I end up coming in on my f of x is an x times an x plus 1, and now I can compare coefficients to get that last factor. So I'm going to have an x squared at the front to get back to it, a minus 6x, and a positive 8. That is going to factor further, which I like. If it didn't, though, then I'm just using quadratic formula. And I come in on that being fully factored, and therefore I know that x equals 0, -1, 4, and 2 are my roots. So now I want to go through and put on a quick set of axes. I can label all those roots. I'm trying to be somewhat proportional on my x-axis. And now I'm going to use leading coefficient and degree to determine my end behavior. So when I look back up to my original, I have a positive leading term, so I'm going off to the right. I cross all of those normally, if you want to think of it that way, because all of those factors occur once. I look at the degree and I notice it's a degree 4. An even degree needs to go off in the same direction in both ends. That one does. I feel pretty confident. In fact, I really feel confident because the only other thing that I have to go through and label is my y-intercept, and I've already done that because I have my graph going through the origin. So my picture's complete. You are good. Hopefully we match up, and we're good to move on to the next one. Okay, so now we take a look at B. We've got f of x equals -x cubed plus. Okay, same thing. You should have tried this one on your own. So this is what I was talking about of if we hit a snag on A, and now we've got it straightened up, then go back to that screen where you have all of them and give it a shot again. Okay, we're going to work our way through. I take a look, it's a cubic. I want to factor it by grouping, but it will not. So I'm going to work my way through then a little bit of factor theorem. So, and I'm looking at a value to sub in. Well, if I sub in a -1, then my first term becomes positive. And my second, no, but then that's not going to give me. I'm trying factors of 3. If I sub in 1, oh, well, 1 actually works. And therefore, x minus 1 is a factor. Okay, so therefore, f of x is now an x minus 1 times my other factor. And so in this case, I need a -x squared at the front. If I went to expand that, I have a positive x squared. I need to get to 6 of them, which means I need another 5 of them. And then I have a -3 as my constant. Now, we may have got to this point, but in 2 different directions. But we take a quick peek into that second factor. And even though that x squared term is negative, we should be able to tell pretty quickly that that is not going to factor further. And so my recommendation to you would be factor out the negative from that as we jump in to use quadratic formula. So what we end up having then is we have an x equals 1 root from our linear factor, and x equals 5 plus or minus the square root of 25 minus 12 all over 2. That doesn't simplify any further. There are your roots. So we can now go and put on our quick set of axes, and I can label all my roots. Well, 1 is pretty obvious. Now, my other ones are 5 plus or minus root 13 halves. You need to label on your exact roots. Do not, absolutely do not label on an approximate. But I do understand that most of you guys are going to push buttons to figure out what those approximates are. Just be very careful. I see too often the people who use their calculator end up labeling with an approximate, and you're going to lose 4 marks. So instead, I'm going to say to you, why not just estimate them? Use your head. You can do it. Let's look at the root 13. Well, root 13 should be 3 point something, because 13 is in between 9 and 16, and those perfect squares, when we take the square root, would be 3 or 4. So I got to be 3 point something. So let's just keep doing 3 point something. So you have, in the addition case, 5 plus like 3 point something divided by 2. Well, then that's 8 point something divided by 2, which is 4 point something. Like, we don't even need to write down that red. We have the ability to do that. Oops. And so, as you work your way through, we now know that you should be good to be able to label 5 plus root 13 halves all the way out here somewhere, because that's 4 point something. Okay, let's do the negative case. So I know that root 13 is 3 point something. So if I now take 5 minus 3 point something, then that's going to get me to a 1 point something. And if I have 1 point something over 2, we should see that that has to turn into a decimal that starts with 0 point something, because my top is less than my bottom. It's going to be a positive value, so I can now label right in here somewhere, that being my 5 minus root 13 halves. And there we go. Okay, we're going to go through and we're going to sketch that thing. And so my eyes now go back to my original function. What was my leading coefficient? It was negative, so I am going down. All of those roots appear once, so I cross like normal. The fact that I then go up this way, because it's a cubic and I go in opposite directions, that matches up. The only thing left to do is to now label your y-intercept. And if we go to label our y-intercept, there's the location, and we should very quickly be able to determine that it is 3. Now, I just want you to take a look at that graph for a second. Do not be alarmed by the fact that your scales on your opposite axes are not the same. Like, just pretty quickly, we can see this is a movement of 1 unit on my x-axis, but it's a movement of 3 on my y-axis. And it looks like the 3 is less than the 1. We don't care. Because we're on different axes, we can have different scales. We just want to be proportional, or as best as we can, on each axis. Okay, hopefully our picture matches up, and we're still doing well. Let's keep moving. Now what you see on the top is there is your set of points. And so we're going to jump to a slightly different algorithm because we don't know the degree of this function. So we should be pretty good to be able to start off and do a little finite difference work to figure out. So the first thing I do is I look and I see I have consecutive x values. Nice. Then I just need to take one point and subtract the point that occurs before it. This is the one where you go, oh, you really want to make sure you do not make a mistake on something like this, because that would be so frustrating. And as I said during our finite difference day, this would be a case where I would be fine with you using a calculator. Okay, subtraction is not difficult. We do want to make sure that we are correct. Silly human error issues can drive you nuts. Well, it's not linear and it's not quadratic, but when we do get down and we notice that as I find my third differences, they are consecutive, I could then draw the conclusion that I am degree 3 or cubic, however you want to think of it. Okay, we get to that point, and now what I want to do is I want to make sure that we are as efficient as we can be when determining the equation. And so just to give us a little more space, there are our 6 points, and we've determined that that was cubic. So the next thing that my eyes want to go to is to what I just starred. That point is going to be so helpful for us because we see we have a y coordinate of 0 that's telling us we have an x-intercept. And so rather than me defaulting to ax cubed plus bx squared plus cx plus d and having to do a lot more work, I can avoid all of that by using that x-intercept. So let's get rid of all of that and let's be a little more efficient. We know that our function has a factor of x minus 3 because of that red point, that x-intercept. We also know it's cubic. Well, right now, my f of x is a degree 1. That means I'm missing 2 other degrees in that function. So what I'm going to do is I'm going to use the most generic second degree factor. I'm going to use my quadratic. There is my function. And now my eyes should go to my y-intercept, because if I sub in 0, then I know my function has a value of negative 24. And I just solved for my value of c. It's 8. And so the version of the function that I want to use now has a factor of x minus 3 and a somewhat generic factor, but we've now solved that c value is 8. Okay, the nice part is I'm missing 2 variables. I'm not missing 3. So my system is going to be easier to solve when I create it. Let's pick 2 other points. So I think I'm going to pick my points that have an x value of 1, because subbing in 1 and calculating is nice and easy. I just work to avoid any sign mistakes. So since, and if I use the first point, then I know that my y value of negative 30 exists wherever I sub in an x value of 1. I would recommend to you divide out the negative 2 and let's actually simplify it down to that point, and we'll call that equation 1. Okay, I can do the same thing now and select my other starred point, f of negative 1 equals negative 12, because my function value is negative 12 when I replace all of my x's with negative 1. I can deal with the same thing and simplify it by dividing out that common factor of negative 4. And there is a simplified version of equation 2. We get to that point, and we should be pretty quick then to solve. Like maybe I take equation 1 and I add it to equation 2 right now, because that's going to allow me to eliminate my b's. And now I can go through and I can sub a equals 1 back in. And I'm going to sub that back into maybe equation 1. So I get 1 plus b equals 7, and so b equals 6. And that's what allows me to create my function. I just found out that f of x is equal to x minus 3. And then my quadratic factor has an a value of 1, a b value of 6, and a c value of 8. And there we go. So hopefully not too bad. We've built the equation for it. All that's left to do is to sketch. So let's go ahead and build a sketch. Okay, so now we have that function. Let's produce our sketch. Quick set of axes. We can look at it and we can say, well, I recognize that that last factor will factor further. If it didn't, then we're using quadratic formula. And therefore, we solve for x equals 3, -2, -4 as our roots. I can now label those. My -2, double that distance is 4. Somewhere in the middle, I don't really like that. Maybe something like that is a 3. My leading coefficient, if I expand it, would be positive. So I'm rising to the right. All of those factors appear once. Ooh, yikes. So I can connect those. And now the only thing to do is to label my y-intercept. Well, if I sub back in and I look, to find my y-intercept, that means sub in 0. That we can solve for that to be -24. However, look back up at your set of points and notice that we were told, again, that our y-intercept was -24. And so the nice part, maybe, about being given a set of points is you actually have something to confirm against. Like I actually feel very confident then that my sketch is pretty good, because when I calculate my y-intercept, it matches with my original point. So hopefully not too bad. We're going to knock out 2 more sketches. So let's take a look at D. D we notice is a quartic. We've been given the equation, so we need to find our roots. Okay, well, I do notice that if I factor by grouping, then I can fully factor that function and get down to there. Okay, we need to have a discussion about what you choose to show, and if you choose to show certain things, what you're then committed to. So, pretty quickly, I hope we would be good to be able to state that x equals 3 or 1 as your roots. And we can see that from solving each of those factors equal to 0. However, I may have had a number of people that would have factored further on that cubic factor, because you say, hey, there's a difference of cubes. And so I know that I'm going to get x minus 1 as my first factor and square it, change the sign, double it. You can see your solutions on x equals 3 or 1 from the first 2 factors. However, what we notice, that third factor did not give us any real solutions. Okay, why? Well, because if I went x equals, and I use my quadratic formula, my 1 plus or minus the square root of 1 minus 4 all over 2, 1 plus or minus the square root of -3 over 2, we can see that we get no solution in that case because we have a negative underneath our root. Okay, what are you committed to? Well, if you wrote down the gold and you have that factored, fully factored, then you must show me the red. because you have created another factor, and you have to prove to your reader that that factor does not yield real solutions. However, I'm hoping that we can see that anytime we have a sum or a difference of cubes, that second ugly factor will not lead to real roots, ever. And so, to make sure we're good with that on why, I want to go through and I just actually want to build something pretty generic. It's going to look really weird because I'm going to pick some weird stuff. But hopefully when we see it, we'd be able to work our way through. So, I want us to imagine that we have a difference of cubes. And so say it was something like this, but it doesn't even matter what the original difference of cubes is. What matters is how we factor it. So I want you to imagine that instead I'm going to change that last term. It's not going to be a 1, but instead it's going to be an h cubed. That is a really ugly h. That's better. If we were to then factor that, then we recognize that our first factor would be x minus h. Okay, so now let's build the second factor. Well, the second factor is going to be x squared. Multiply those together and change the sign. Square the last. Now, why is that important? Because what we're going to do is we're going to now take that last factor and we're going to use quadratic formula on it. So therefore, x equals negative h plus or minus the square root of. But can I even shorten this down more? If really what we're focusing in on is the fact that this is going to give us no real roots, then let's just examine what's underneath the root. So let's just examine the discriminant. Okay, well, what does b squared minus 4ac look like in this instance? Well, I'm going to get an h squared minus 4 times 1 times c, which we can see is going to simplify down to this. And I'm hoping that because we dealt with that difference of cubes in purely generic terms, right? There was no constants in there, it's just all variables. That maybe you can see that because the second factor, this big second factor is built by multiplying the two things together, but then the last one is always the second thing squared, that even though in quadratic formula we square the middle coefficient, we're always going to have that same squared in the end. Also, because it is a perfect square, it will always be a positive, and therefore in quadratic formula we will always be subtracting between. And then you have your good old 4 part of your 4ac. That every time you use the discriminant on this difference of cubes or sum of cubes, your second term will always be bigger than your first. And so if it's always bigger, then it's never going to yield real solutions. So I would argue to you, let's erase it all. And if we're stuck having to go through and show that it gives us no solution, either by using quadratic formula or the discriminant, then why even waste our time factoring that? Why not just do the blue? So be very careful. If you choose to factor it further, then you are fully committed to showing all that work. Instead, let's just go through and solve for our roots right as we see them. Okay, now that that is the case, we can pick up the pace. We now have our set of axes. We have an x-intercept of 1 and an x-intercept of 3. If I go through, look at my leading coefficient, it's positive, so I'm rising to the right. That root of 3 shows up once, so I cross like normal. However, that root of 1 shows up once, so I cross like normal. Don't make the mistake of thinking that it shows up a cubed number of times. No, it doesn't. That root only shows up once when we solve the equation. That maybe then this is our picture. And you're good. All we need to do is label our y-intercept. Oops. And there you go. But we also noted from before that you can have some other sketches that because we did end up with some complex roots, you may have had your 3 and your 1. And we just know that there may be a slight change of direction somewhere else, but not near the x-axis. And so maybe we end up in this instance where we come down and then we get something like that. The details of your sketch, as we said, we will fully get them as soon as we mix in with some of our calculus. Okay, hopefully we got something like one of those two or other options. There we go. Last problem. This one should look familiar because I actually threw it up at the end of a lesson. Now we have a chance to talk about what it should look like. So we should be able to go straight to a sketch right now. And even though it looks really ugly, it's actually pretty good. We notice that we're going to have x equals -1, 2, and 3 as our roots. So my x value is -1 at 2 and at 3. If we were to expand it, we're going to have a positive leading term, so we're rising to the right. Now, that root of 3 shows up 3 times, and so I have to make sure that I go steep to flat to steep. My root of 2 only shows up once, so I have to wrap around and try not to become vertical, right? This is a function. I have to pass the vertical line test. And now as I come around, I notice that that factor of -1 shows up twice. Therefore, my curve has to be tangent at the x-axis. And maybe I get something like that. Okay, only thing left to do, label on that y-intercept. We can do a quick little calculation, knowing if we expanded it, it would be the constant at the end. Or if we sub in 0, then I'm going to get 1 squared times -2, and then -3 cubed, which gives me my -27. And so if I calculate that, I get my 54. I get a little confirmation. There's my y-intercept, and we're good. Okay, you've now gone through and you have sketched a bunch of different problems depending on what form they're given to you. Job now is to make that algorithm automatic. There's lots of room for silly little mistakes, so take your time, but the second you start to feel really comfortable with it, start to try to push, go as fast as you can, risk some mistake. Okay, good luck with your practice.